Hello, everyone. Thank you so much for joining the Aquanti team for today's webinar on next generation hydrological forecasting, AI-driven insights for a changing climate. Please note that this webinar is being recorded, so I'll thank you in advance for keeping your microphones muted until the end of the presentation, where we will have plenty of times for questions and discussion. My name is Braden McNeil. I'm the Technical Sales and Marketing Lead here at Aquanti. I'm really just here to provide a brief introduction for today's speaker, which is, of course, Dr. Andre Erler. Andre is our senior climate scientist here at Aquanti. His main expertise lies in regional climate modeling and applications to hydrology and hydroclimatic extremes. Originally from Germany, he received the equivalent of a master's degree in meteorology from the University of Mainz, followed by a PhD in physics from the University of Toronto in 2015. For his dissertation, he performed high-resolution climate simulations for Western Canada and studied hydrological impacts of climate change in the Athabasca and Fraser River basins, as well as changes in precipitation extremes due to climate change. Andre joined Aquanti in 2016 in order to study the impact of climate change on water resources and agriculture in Canada and provide insights into climate change impacts to end users. And for the past 2 years, he's been the project lead and key developer of Hydrosphere AI, which is Aquanti's latest innovation for machine learning-based streamflow forecasting. Andre, thanks in advance for a great presentation today. I'll pass the mic over to you.
Yeah, thank you. I hope everyone can hear me all right. If not, please complain. And yeah, thanks, Braden, for the introduction. As you said, I'll be talking about Hydrosphere AI. And yeah, that's our new AI-driven streamflow forecasting system. Before I get to the modeling side and the skill of the models and how all of this works, I'll talk a little bit about Aquanti and where we are coming from, also in terms of real-time forecasting and what we have in terms of experience there. And yeah, then I'll talk a bit about the model architecture, the background, why and how this works, what skill we can achieve. And then in the second half, I'll also talk about our real-time forecasting platform and how we've implemented these AI-driven forecasts. And so what use you can get out of it and how the infrastructure works in the back end as well. There will be time for questions at the end, so you can probably hold them and probably also write them in the comments. Braden will be moderating the Q&A session at the end. So with that, I'll start with the presentation. So the wait just a second. Okay, good. Let me just get the controls right here. So, yeah. So, let's start over again. So, Aquanti is a spin-off company from the University of Waterloo, and when I started, we had about 7 people, I think. And now we've grown to over 30 people, and mainly we come from the consulting modeling side in the hydrological space, but then we've also moved a bit into real-time forecasting. So the original Aquanti product, is this moving forward? Yeah. So yeah, the original Aquanti product was Hydrosphere. That's an integrated hydrological modeling software or model. And most of our initial product and project work was built around that. And since then, though, we've expanded into forecasting, and initially we've mainly also based this on Hydrosphere and sort of built a forecasting platform around Hydrosphere. And this is now hydroclimate side, where we actually have a fairly broad suite of offerings for both real-time data services as well as scenario modeling and forecasting. And that's under the umbrella of hydroclimate site. And of course, originally we come from the research community, and we've done initially a lot of research in hydrology and climate change impacts, and we've published on climate change impacts on groundwater and soil moisture. And So that used to be kind of our bread and butter, but then we realized that we can also apply this to real world problems. And initially, most of this again was most of the work that we've done was on the real time. Or was with Hydrogeosphere in different project work, and for some reason I have to say the transitions don't work properly. But yeah, okay. Most of our initial work was with Hydrogeosphere doing project work in various industries, so in water resources, climate change impact assessment, but also in mining and agriculture, and then also tracer work and contaminant transport. And then with all this project work, we've wrapped it into a real-time platform, and a lot of this is now available as HGS real-time, so HGS RT. But so now we essentially have 3 pillars in the company of work that we do. We have Hydrogeosphere, that is the model, and we're still developing this and supporting it, and you can get licenses here for Hydrogeosphere. Then we have Hydroclimate Site, which is our online offering that includes Hydrosphere AI. And then the third pillar that I'll mention a couple of times today as well is Canada One Water. That's sort of an umbrella project that houses a lot of our academic collaborations, and big focus is to develop a hydrological modeling framework for Canada that also includes groundwater and climate change impacts. And so I do a lot of work on the climate modeling side in this project as well. So with the Aquanti real-time platform, we've deployed this in several parts of the country, and this is our little map that shows where we have Hydrogeosphere real-time deployments. This is in Alberta, and we've actually added a few more watersheds here in Alberta. Then in Manitoba, with MFGA, we have a large deployment, and then several in Ontario, in Southern Ontario, as well as South Nation watershed. In near Ottawa, and we are also adding Barbados now, which is pretty interesting. And this is all under the umbrella of Hydroclimate Site. But it's not the main topic of the talk today. This is more sort of the background where we come from with hydrological forecasting. But today I'll be talking about Hydrosphere AI, and the motivation for this was really that the physics-based modeling in real-time forecasting is relatively expensive, and in that the models take relatively long to run, but they're also quite labor-intensive to develop and calibrate. And so there was a clear need for something that's more scalable, more lightweight, but still offers good forecast skill. And that is what Hydrosphere AI offers. It's focused on streamflow forecasting as opposed to sort of a holistic watershed simulation that we have with physical models. But in most cases, that is enough, right? That's what most people are actually interested in. We do have some other forecast endpoints as well. But yeah, so the advantage of Hydrosphere AI compared to most other real-time forecasting that we've deployed so far is that we have really good coverage. So we have data sets that cover essentially the entire content, even more than is shown here. The models we are using run really fast. They're state-of-the-art based on LSTMs, and I'll talk more about this in a minute. And then it is built on, or the forecasting platform is essentially built on the same weather forecast that we are also using for physical modeling. So this is essentially the weather forecast from Environment Canada, JEPS, and HODPS. You may have heard of those. We also pull in other real-time data. And forecast horizons are daily, hourly, up to seasonal. And this is all offered through our web platform, and in the second half of the talk, I'll show some screenshots and sort of present how that looks like and how the forecasts are delivered. Right. So before we start with the ML models, a little bit of history. The idea of using machine learning forecasts for essentially rainfall and runoff prediction is not radically new. This has been around for a while. It is, in a way, a very obvious idea when you think about that. Rainfall runoff models, historically, the conceptual rainfall runoff models are heavily calibrated, and the way they are used, it is essentially a machine learning problem where the structure of the model is highly constrained by physical insight. The main issue or problem why this has never really gotten to prominence until very recently is that in most cases, researchers try to train models for a single watershed. And in a single watershed, you don't have enough data to really constrain a very flexible open model structure. And then you either get very poor skill or you get overfitting. And this has changed recently, and there were essentially two major innovations that significantly improved the skill. And both of those were introduced by Frederik Kratzert in 2018 in a seminal paper that now has thousands of citations, and that our work is essentially based on as well. These two factors are the use of LSTMs, so long-term, short-term memory systems, which have a memory cell. So this is really important so that they can represent the state of the watershed. So this is a model architecture. And then the availability of large homogeneous data sets that are labeled. And this is a relatively common story in machine learning, right? So now the academic focus has moved beyond this and is mainly on evaluation or of the models and sort of learning how they're behaving in a historical simulation context, but also the interpretability and explainability, and that is a big factor. And of course, that is important. But what we in the company are focusing on is the real-time operational deployment of these models, and that has additional challenges that I'll talk about a bit later. Okay, so why LSTMs? And I've alluded to this, they have a memory cell, and this in a way makes them very analogous to physical models. So they are time dependent. It is not like what you would have, for example, in a random forest where you just have some input values and you get an output value. You really run these LSTMs over time steps in a very similar way as a physical model. And so because of that, they are able to track snowpack and like soil water content and really physical quantities. They don't do this explicitly, but they learn how to do it. And you can show that that is actually what they're doing internally with the memory cell. This also means that they actually need to be spun up like physical models. That seems to be a bit counterintuitive to people who initially learn about these. But you can think of them in almost as drop-in replacement for a conceptual rainfall runoff model. They also follow essentially an HRU approach. So they essentially simulate a catchment as lumped. So as a bit of trivia, these LSTMs actually come out of natural language processing, and they're often used in time series prediction, but in a way, they're also a very distant ancestor to chatbots like ChatGPT. Yeah. So the other important part is, of course, the training data. And initially, this was camels, which is a data set that was only available for the US. And so this is where this figure is from. For North America, there's now HYSETs. And so that's the main data set for Canada. It is very heavily reliant on ERA5. So ERA5 is a commonly used and really very good reanalysis. But ERA5 does have some issues, especially with precipitation. And so we've actually added a lot of extra data to this HYSETs data set. We mostly use Ag ERA5. That's a downscaled version of ERA5. And Kappa and HODPS, for real-time data. We've also augmented the available streamflow data from HydAT, and a lot of the static data, and this is actually very important, and maybe I should emphasize this a bit more. There's dynamic data, and then there's static data. Dynamic data is the weather data, and static data is land use data, topography, like static attributes of the catchments. And a lot of this we can actually draw from Canada One Water, and this has been extremely beneficial because with that we have wide coverage and really high quality data. As I mentioned, the models essentially follow an HOU approach. So all these data are always averaged over the catchment. And most of the catchments that we'll look at are quite small, so this is quite easily possible. And the models are also trained over all of these catchments at the same time. So they're not trained for any specific catchment. And this is also important to keep in mind. And this was really one of the big innovations as well. So you're not training for a specific watershed. As I said, there's not enough information available, actually. So you have to train and learn the physics by training over all of North America. So, come on. Yeah, so Canada One Water is extremely beneficial here. And so to put this all together, we need essentially two components. We need the trained models, which are trained on all watersheds, and they have this specific architecture with the memory cell. Then we need to put this together with weather forecasts in order to generate actual useful forecasts, right? So if you just do historical simulations, that's not really useful. So for operational forecasting, we need to combine this with operational weather forecasts, which come from essentially Environment Canada or can also come from other providers. And those also need to be aggregated over catchments. And then the output is daily stream flow. And so most of the models I'll be talking about produce daily output and primarily stream flow. We'll also see that there are some other options as well. But unless otherwise noted, it's daily stream flow. Okay. And so let's talk a bit about the skill that we can achieve with those models. It's actually, it's pretty impressive. And so this is based on historical evaluation. These, the models I'll be talking about here are trained primarily on Agera 5. And then we'll also talk a bit about fine-tuning with Kappa, so that will come next. The static attributes are, as I said, from Canada One Water, and the gauge data is from HydAT. And what I'm showing here on this graph is the skill distribution for the model. So on the x-axis is NSE, that's a Nash Sutcliffe efficiency. And this is averaged over an ensemble. And on the y-axis is the cumulative distribution function of the skill. So we essentially want to have this curve to be as much on the right-hand side as possible. So what we see here is that there are two different lines. The blue line is LSTMs evaluated in basins that they have seen before. They're not calibrated specifically for that basin, but in the training process, that basin or catchment was used. And then we get a skill of 0.73, so that's pretty good. And this is typically what you will have with a conceptual model, right? The conceptual model will have been trained on a catchment that, where it's also used. So it's not an ungauged prediction. Also interesting is this green line. And this is if we evaluate the models only in catchments where they have not seen during the training process. So they were withheld from the training process, and this is done with cross-validation then. And so this is essentially the skill in ungauged basins. And we still get 0.665. And so this is also pretty good for an ungauged basin prediction. So we're pretty happy with that. And it actually means that these models can actually do ungauged prediction, although gauge prediction is, of course, better, right? Then we can also assimilate observed streamflow data. So if we do gauge prediction, that means there is a gauge. Usually the gauge also has real-time data. And this can be used to improve the spin-up of the models. And so the orange line here, this is what we call a QLSTM. It's an LSTM that actually gets the streamflow, the previous day's streamflow input, and then does a prediction with that additional information. And then we get a skill of 0.84 almost. So that's very high then. And so this is actually what we've typically deployed in all of our Hydrosphere AI deployments at the moment. So they do assimilate observed streamflow, and that significantly improves, especially the spin-up. Of course, during forecasting, that's not available. It's obvious. Okay, so let's look at what the distribution of that skill is. It's not uniform across the country. And here we're just showing Canada, but we do actually have US gauges as well. And so green is very good skill, and then white is mediocre skill, and then red is poor skill. And you can see that in British Columbia, for example, but also in Northern Ontario and in Quebec, we have really very good skill, so mostly above 0.8. And these are snow-dominated catchments, and we typically do best in those snow-dominated catchments. The worst skill tends to be in the prairies, so most of them are just mediocre, and some of them are actually rather poor. And also, subpar skill is actually in some areas of Southern Ontario, and that is something we're actively working on at the moment. There is a lot of human influence, so that is often hard to capture. There's also there has been a lot of development over time, and this is something that the models also have difficulty with, because we're treating catchments as relatively static during the training process, but in Southern Ontario, that's really not the case. Then there's also the observation that both in Southern Ontario as well as in the prairies, runoff behavior is very flashy, and the catchments can be quite small. And especially in those cases, and especially when we have convective precipitation, then there are small timing errors, or, for example, and this actually happens quite often, unfortunately, the precipitation event is not captured by the training data. And then there's not really much we can do, but except work with local gauge data and the rain gauge data, and this is actually something we're working towards at the moment. Okay, so with this hint at the issues with training data, so this is with ERA 5 actually, and so ERA 5 has, the precipitation is model generated in ERA 5. We do actually get significantly better skill, and this is now in the purple line, when we fine-tune the models with kappa data. So kappa includes rain gauges and also some radars, and so the precipitation data is a bit more reliable. It is not 100% reliable though, and kappa also changes over time. And so in some cases, it actually makes results worse, but in most cases, it makes the results better. And so this really shows how important the training data is. And yeah, ERA 5 is a bit problematic with precipitation. Good. So in terms of features that we currently offer with Hydrosphere AI, I've already talked or alluded to two of those. One is, of course, the fine-tuning data sets and the augmented data set that we have, both the static data as well as all the work we've done into to put together real-time weather data. What we can also do is actually do predictions at any point along a river. And now I've always shown comparison to gauge data, but that is, of course, just for validation. So we can make synthetic gauges, if you will. But those would, of course, be a prediction in an ungauged basin, essentially. Right. We've also talked a bit about the data integration. So that's essentially data assimilation, if you were thinking about the context of a physical model. And then also integration of rain gauge data. And this is something we think is actually quite important, especially in Southern Ontario. And there is actually a very dense gauge network that is not necessarily assimilated in Kappa. So there's a lot of room for improvement here. We just need to work more closely with our customers here. What we can also offer is different forecast endpoints. So not only streamflow, but also snowpack forecasts and soil water content forecasts. And these are, of course, quantities that any LSTM would track implicitly, but it doesn't output explicitly. And so we've developed models that can output those explicitly. And that actually works really well. So skill for snowpack is very high. It's above 0.9. And what we're currently also working on is hourly models. So this is actually feedback we've gotten from users that the daily aggregation is a little bit too coarse, and hourly aggregation would be much more useful to capture flood peaks. And that's what we've been working on. We're actually going to deploy this probably next week. And with that, of course, it's also a lot more useful for flood forecasting and for high and low flow alerts. And those are actually already implemented in the platform. And then on the other side, we can also do long-term seasonal forecasts, so sub-seasonal and even seasonal up to 6 months. Right. Okay. So with that, I can show some examples of hindcast in this case. So this is a basin in between Banff and Jaspers in British Columbia. So it's a snow-dominated alpine catchment. And what we can see here, if I switch to the laser pointer, is so the top panel is streamflow, and so it's the beginning of the year, and then the end of the year, summer is in the middle, and then the bottom panel is snowpack. So, and the blue lines are observations, or in case of snowpack, it's actually Era 5 land. And then the shading around it is the historical normals. And the orange line is our model simulation. And so in early summer, so this is essentially June, July, we see the spring freshet, and this is of course an alpine catchment, so it's relatively late, and then we have precipitation that's driving streamflow as well, and still late season snowmelt as well. And then in winter, of course, there's not much happening because everything is frozen, but you can see that snowpack is accumulating over the winter, and then it's melting in spring and driving the spring freshet, and then of course in summer there's no snow, or very little snow, right? So we can also show a catchment in Quebec. So this has more of a spring freshet and then as a peak in fall. So it's the same organization here, streamflow at the top and snowpack at the bottom. There's less snow overall than in the Alpine, of course, but it's still snow dominated. And we can see a very strong response in the spring freshet. We're capturing this really well, and typically it is the spring freshet that we're capturing best in snow-dominated basins. In summer, there's not that much runoff, and then in winter, we see that the fall rains are starting and generating runoff as well. But here, there's a bit more uncertainty about the precipitation forcing. All right. Now, the other feature we've implemented, as I've mentioned, are the hourly forecasts. And briefly, these are also called multi-timescale models. The way that this works is, so the challenge with hourly models is that you actually do need to spin them up over a year, right? And then that actually means you have a lot of time steps. And that does get, so with that, we are actually hitting computational limits. And so the solution to this is actually a multi-timescale model that we can spin up over a year with daily time steps, and then about 2 weeks before we actually start the forecast, we switch over to hourly time steps. and do a high resolution simulation. And then when we are at the present, when we are issuing the forecast, then we are issuing the forecast with hourly time steps as well. And typically we would be using a short range forecast for that. On the left-hand side, so you can see an example of these hourly models in a hindcast situation, and this is in Ontario, Northern Ontario. So they do actually pick up quite a lot of variability. So you can see that this is a bit of a difference compared to what I've shown before with the daily LSTMs. They do look smoother. And if you zoom in here a bit, and this is just zooming in the spring freshet, we can see that there's still a lot of small scale variability here as well. This is actually still a relatively smooth streamflow curve in smaller watersheds in Ontario, or even in the prairies. This can look even flashier with shorter timescale variability. Another interesting point here that I want to point out here is this is an apparent forecast failure here where the models are not producing any streamflow, whereas the observations are showing streamflow. But this is actually a situation where this is driven by convective precipitation that wasn't captured in Kappa. And this would really improve if we integrated local rain gauge data through a WSGI network, for example, which a lot of CAs have. At the moment, we're just relying on Kappa, but this is something where we want to work with our customers to integrate that where available, and then this should improve significantly. Now, so in terms of deployment, we are actually running a beta test. We have one that is open basically to the public across Canada, where we have a selection essentially of these high-set watersheds, and it's actually just about 10% of them. And these are smaller watersheds that are running just across the country, and people can look at them. So you could sign up to Hydroclimate site and go to HydroSphere AI and just look at that. And we've been running this for about a year now. And it's primarily to demonstrate how readily deployable and scalable these models are, and how much coverage we can achieve. We can actually now also extend this into the US, although in our beta test we haven't done this. And we're running those primarily with JEPS forecast, so the Global Ensemble Prediction System, and the spin-up works with Kappa and HDPS. But those catchments are all smaller in nature, so only about 2,000 square kilometers or smaller. And of course, in Canada, we do have a lot of rivers that are significantly larger and have significantly larger catchment basins. And but those are, of course, all made up of smaller tributaries. And so for the ML models, because they're really HRU based, and there's a limit to the reasonable size of an HRU, right? We have to take a somewhat different approach with larger rivers. And this approach is essentially to use a routing model, and these are well established, right? So we don't have to reinvent the wheel here. We can essentially link smaller catchment LSTMs using a routing model into larger rivers. And in a very similar way as is commonly done with rainfall runoff models that are also HRU based, right? Another benefit for this is that these routing models can also fairly easily handle flow regulation from, for example, hydropower. You can basically put this in explicitly, right? So this significantly increases the utility for hydropower operators as well. And so here I have an example of where we've set up such a routing scheme. And I should say that this is something that we would typically have to set up in collaboration with a specific user, because it usually does require a little bit of handcrafting, especially when there is hydropower involved or in flow regulation of any kind is involved. This is an example that we've set up in the Peace River as the subbasin, the Smoky River. And so you can see the delineation into subbasins. So we have to discretize any larger basin into a complete coverage of non-overlapping subbasins. that are all smaller than 2,000 square kilometers, but usually they're even smaller, something like 500 or 100 even. So here we have some over 50 subbasins, link them all together with a routing scheme to predict stream flow at that node. That's the gauge here, and this is just from the test data set. And the NSE we're getting, and this is essentially just out of the box, we didn't really calibrate this much, is 0.79, so it's pretty good. But this is expected because it's also a snow-dominated watershed, right? And so with this, I actually want to briefly highlight the potential that this kind of technology has for hydropower, especially in combination with a routing model that can handle regulation scheduling. So in terms of features, we can offer real-time monitoring, but also something you could think of as a real-time digital twin. So even if you don't have gauging in a particular part of the inflow catchment, we could still provide flow estimates based on real-time weather observations or CAPA, or essentially remote sensing or data assimilation modeling, and provide a current estimate of flow, but then also, of course, using weather prediction products, forecast of flow as well, and so this can help optimize reservoir operations and really optimize the efficiency and reduce costs, right? So you can optimize your scheduling and minimize unwanted spill events, but also mitigate risk from extreme weather and sort of help with regulatory compliance. So we think that this technology is really a great opportunity and has a lot of potential for hydropower, and we are very interested in working with hydropower operators to implement this and optimize the way that we are running these models for hydropower. Because one thing we have learned in working with clients is that there are always some different endpoints that every user needs, and so ways we can tweak the models to better serve specific communities, right? Okay, with that, I actually want to talk a bit about the modeling platform and the forecasting platform that houses these models and then disseminates the forecast. And first, we'll talk a little bit about the right-hand side here, so how we're disseminating forecasts and displaying them in our web platform. But then I also want to talk a bit about this black box, if you will, and sort of uncover this a little bit and give you a sort of a peek behind the curtains of how this works and what goes into running these kind of systems, because it is quite interesting. It is not that trivial. All right, and so we are currently running a beta test. We are running the one that across Canada that's open to everybody, but we are also running a beta test with Conservation Ontario, where we're specifically talking to the CAs, and we have deployed real-time forecasting for all of the CAs in Ontario, and 19 of them are actually actively participating in our beta test and have given us feedback. This is super useful for us. We have learned a lot from this. And great shout out to all the CAs who have given us feedback. What we've been providing here is essentially the 16-day daily forecast, but as I've mentioned, a lot of them have given us the feedback that that's a bit too coarse, so now we are deploying the hourly models, and that's really a direct consequence of feedback we've gotten from the users, and we should be putting them up next week. So when you look at the web platform, for example, if you're a CA, this is the Grand River watershed. That's our home watershed, so Waterloo, where we are based, is somewhere here. And This is a figure from a bit earlier in the year during the spring freshet. So at this time, we still had snow cover. So the white purplish color shows the snow cover from snow dust. That's one of our data layers, one of the more popular ones. There are a ton of other data layers as well. So we have MODIS imagery, we have soil moisture, and we have kappa precip. We also have static data layers like the crop inventory and topography. So a lot of data, but we of course also have our forecasts, and forecasts are available at these balloons. So they're time series forecasts, basically HRU based, right? So you have to click on a balloon and then you get a forecast time series. And that looks like this. And this is also essentially how it looks on our web platform. It has evolved a little bit now, but it looks relatively similar to this. So you have a spin-up period where we do have observations, that's the black line, and then the red line is the spin-up from our ML models. And then after the now marker, it's a forecast. And the red line is the median of the ensemble. So it's an ensemble forecast that's based on an ensemble weather forecast that runs over 16 days. And then the green shading is the spread of the ensemble. Right. And then there are a couple of other controls here as well. And at this point, we actually have a couple of more models that you can select from as well. Yeah. So this is what you would see if you would sign up for the forecast or for the platform. And so now I just want to show a case study that we've done. This is essentially an event from earlier this year in March. Or at the end of March and early April, where we had a lot of precipitation. And this is not snowmelt driven, it's really precipitation driven. And so in the lens here, you sort of see the precipitation system moving through in kappa. So this is just daily kappa. And then on the left-hand side, you can kind of see how the forecasts are progressing. And these are actually not always shown at the same time, but you can see how as we are moving forward in kappa, you can also see how the forecast issue date is moving forward. So the event essentially stays static, that's the black line, and then the forecast funnel of the ensemble is kind of moving closer, and as it's moving closer, it's becoming narrower and narrower, and then we get to the event. And so I'll just stop the video now and move to the next slide. And this is one of those forecast stations. This is Dingman Creek. This is near London, so in southwestern Ontario. And there was actually a flood warning that was issued by the Conservation Authority. These are just some benchmark values, which are also for 2 and 5 year floods. Those are also shown here with these lines, the blue lines. And this is the forecast from about 10 days out, right? So yeah, it's there's a lot of uncertainty, of course, in this forecast. And so the actual event occurred here. The black line, as a reminder, is the actual observations after the fact. And then the red line is the forecast median from 10 days out with the forecast from that time. And so you can see there's a lot of uncertainty about when the event will occur. Some members showing earlier, some later, or what the magnitude will be. But the actual event was actually within the range of uncertainty here. And if we move closer to the event, the forecast changes as the weather forecast changes, and but it narrows a bit. And the closer we get, the closer or the narrower the forecast funnel or the uncertainty funnel is, and the closer we get to the actual magnitude. But one thing I'd want to point out here as well is the actual event ended up being sort of spread over 2 days. And this typically happens, so these are daily aggregates, when the event sort of happens at the end of the day of the first day and then spills into the next day. And then you get essentially 2 days that have some magnitude. Whereas with the forecast, there was a bit of a timing error, and the forecast put the event more on the first day, so that the total accumulation on the first day is higher and then the second day is lower. But this difference here is actually primarily a timing error that comes through the daily aggregation. Right. So if we want to move closer to that, the forecast funnel narrows and the forecast becomes more accurate, right? And now we are essentially in the event, and now the spin up and the real-time data integration actually becomes really important. And we have to keep in mind that Kappa actually has 1 day lag, so we have to stitch this together with a forecast. If we had real-time gauge observations that would come in, that would be even better. And so at this point, then the spin-up becomes absolutely critical. Before, the spin-up wasn't as important because there was just not that much happening before, right? But if you have a couple of events back to back, this real-time spin-up is critical. And so I want to talk a little bit more about this here. It's really important to emphasize that it's not just the forecast. And so the forecast I mentioned is from GEPS, so the Global Ensemble Prediction System, but the spin-up is HydroPA, that is Kappa, and then we also use the meteorological analysis from HRDPS. And so we use that for variables like temperature and surface pressure and wind. There's not just precipitation that drives these models. And actually solar radiation is another important one as well, especially in the snowmelt season. And we heavily rely on this data set that we are assembling from Kappa and HRDPS. We're essentially extending this every day. And then when we run a model, we're taking the last year to spin the model up from this data archive that we are assembling. And then we are transitioning it into the forecast. And as I said, in this case, mostly GEPS, but we can also use, and we will use for the hourly models, the HRDPS forecast, which is a 2-day forecast, but has hourly data. And it's generally more accurate especially during the convective season. But then we can also use HER, that's a US product, or NAM. For flood forecasting, HER would actually be very attractive because it also has integrated radar, and it's actually only an 18-hour forecast, but a new forecast is issued every hour, so that if we have a reliable and high-resolution real-time spin-up, ideally that includes rain gauges, then we could issue a new forecast based on HER every hour. So essentially as an event unfolds, right? Requires a little bit of data infrastructure and also collaboration with the CAs and other users that we are really looking forward to. So this data integration is really an integral part of our platform. And so there are for forecasting, there are really two important data sets. One is the near real-time spin-up data, and then the weather forecast, right? And then that means overall for this entire endeavor, there are actually 3 different types of dynamic weather data that are critical. The first one is the historical weather and climate data that the models are trained with. This is, of course, super important. Otherwise, these models would not work. But this is essentially where academia today stops, right? And then for real-time forecasting, you need the near real-time data, and then you need the numerical weather forecast or AI-based weather forecast at this point, because those are actually very good now. But I would say arguably the near real-time weather data is the most difficult and requires the most infrastructure. And in terms of infrastructure, this of course all has to be automated. So we have everything running on schedulers that pull in the real-time data in regular intervals and also pull in the forecast, and all of these workflows are automated. So we have an automated download workflow or API query workflow. Then there's a lot of data transformation that has to be done to extract the relevant variables, to reproject them, clean the data, store them in more useful formats. And this is true for both the gauge data as well as the weather data and the forecast data. And then we have to archive this. We have to assemble our own spin-up data set. And then we also have to serve the data in our web platform. So there's a cloud database involved as well. So there's a lot of infrastructure. And I do want to highlight the weather data a little bit here. This is really a big part of the platform, and that requires a lot of work and a lot of development, and also a lot of specialized knowledge. So we have to download these script files, and this is a special format that's used in weather forecasting, gridded binary from Environment Canada. We have to compute the relevant variables that we need for our models. Then we need to clip and reproject this, regrid this to our area of interest. An important step for physical models is also downscaling and bias correction. Also, lapse rate adjustment based on a high resolution DEM. This is very important for snow modeling. And then, of course, for the ML models, aggregation to the HRUs or to polygons, resampling to daily or hourly. But this is actually all very similar for physical models as well as for the ML models. And it's especially important, the statistical downscaling part is especially important for seasonal forecasts because those have typically lower resolution. Yeah, for the ML models, it's more the aggregation into HRUs. And the near real-time spin-up data, it's really important too. But that's also important for the physical models. Okay, and so I'm almost done now. Quick word on interoperability and the scalability. So the ML models are really highly scalable. This is one of the main reasons we've started this development, and they can be deployed very easily almost everywhere. We've also put a lot of work on integration with other tools that are used in the industry. We have web APIs that can be queried, and we can also export into a bunch of different formats. We have worked with kisters that we can export into ZRXP files. Of course, we support typical GIS formats. We can also upload data to an FTP server if somebody needs that. We can produce output that can be directly ingested into HECRAS models or into Delft Fuse. And of course, we have our own web platform as well, and we can work with clients to accommodate different API access. And that essentially brings me to the end. I just want to highlight the main points here. So these LSTMs need to be trained on large data sets, but they achieve very good skill. They can actually do prediction in ungauged basins as well. And this surprises a lot of people because machine learning models need to be calibrated, of course, but they actually also generalize really well. And especially in snow-dominated basins, we have pretty good skill. Additional features that we've developed on top of what you would typically find in the literature is forecast endpoints for snow and soil moisture, as well as data integration and hourly short-range forecasts. And we can also handle larger streams using routing models, and those can also handle streamflow regulation for hydropower generation, for example, or other purposes, flood control as well, or irrigation water supplies. Yeah, and as I hope I've illustrated just now, there's actually a lot more than just the AI models that goes into this. There's a lot of infrastructure that actually also requires a lot of domain expertise and not only expertise in these AI models. But this is already something that we've developed, and we have the infrastructure for that. So we've got you covered there in case you need that. And with that, I can open the floor to questions.